All right, here we go. Quadratic inequalities. We're going to solve quadratic inequalities also graphically, and then we'll solve those algebraically too. So let's get rolling. So solve quadratic inequalities graphically. We're going to take the single inequality and separate it into two equations, just like we've done before. So not a foreign idea there. So we're going to separate it into two, and then graph those two equations and figure out where to shade, kind of like, or figure out where exactly is one equation greater than or less than the other one. So depending upon what we're working with. What does this look like? Suppose we have the quadratic inequality. 3 times the quantity x minus 1 squared minus 5 is greater than 7. We're going to split these into the two equations here, and we're going to graph each of these things. So we're going to graph this parabola, this quadratic equation, and then graph the line y equals 7, or g of x equals 7. What does that look like? It looks like this. So here's the parabola. 3 times the quantity x minus 1 squared minus 5. Notice the vertex is at 1, negative 5, as we can tell from our vertex form. Then we can just plug numbers in and see what we get out. We can plug in 2, we can plug in 3, plug in 4, and then reflect those over the line of symmetry. That's where the parabola comes from. Then we graph the line y equals 7, or in this case, g of x equals 7. We're using function notation. Then find out where those lines intersect. If you make your graph precise enough, we can see that they intersect at this point. Negative 1, 7, and 3, 7. So therefore, the solutions to this inequality are kind of at these boundary points here. But we want f of x, we want the blue function to be greater than the red function, because it says that f of x here is greater than g of x. So we want to look for intervals on the x-axis where the blue is above the red. And from there, it's going to be from 3 and on, 3 and bigger, or from negative 1 and less than that. So that's where this comes from. The solution to this is x has got to be less than negative 1, and it's strictly less than because it's not an or equal to. So if we go this way, this blue will continue to go up, and the red will stay the same. So x has got to be less than negative 1, or x can be bigger than positive 3. That's what we're doing here with looking at that. So what does that number line look like? Where do we shade on a number line? The number line solutions would look like this right here, where we have 3 is not a solution, but it's the boundary point. Anything bigger 3 will make that quadratic inequality true, and anything less than negative 1 will make that quadratic inequality true as well. So algebraically, what does this look like algebraically? Well, we have our quadratic inequality. We're going to isolate the squared expression again, and then decide whether the inequality can be solved, keeping in mind that squares can't be negative, and write it as two separate inequalities. So you've got to kind of remember a couple of those basic ideas. Now, when we separate the inequality into two, we want to flip the inequality sign when you flip the sign of the number. So that sentence is actually very confusing, I think, when I say it out loud. But once we see what this is meaning and what happens there, I think that'll become a little bit more clear. So let's first isolate the squared expression. So basic algebraic steps here. We're going to add 9 to both sides, make that 7 into a 16 and get rid of the negative 9. Then we're going to divide by 4 on both sides, and we have x plus 3 squared. This quantity needs to be bigger than 4. So we have to ask ourselves, well, what numbers can go in here to make this bigger than 4? So something else we could do here is just get rid of the squared. We could take the square root of both sides. So if we square root, take the opposite of the square, we could square root that, and we can get x plus 3. If we take the square root of 4, that could be 2. 2 times 2 is 4. But negative 2 times negative 2 is also 4. So what this sentence is saying is that when we flip the inequality, when you flip the sign of the number, this positive number became a negative number. So then this sign will flip and become a less than. So what that means is that we want numbers that are less than negative 2 inside this parenthesis. We want a negative 3 to be in here, because if a negative 3 is in here, negative 3 squared is 9, and 9 is bigger than 4. So that's what happens when we have that negative And the sign flips because we want numbers that are smaller than -2, because when we square those numbers, they will end up being bigger than 4. So that's what's happening and why these signs have flipped, because these two types of numbers will make this sentence true. And then we just solve these inequalities algebraically. Subtract 3 on both sides of each of them, so we could say that x has got to be bigger than -1, or x could be less than -5, would be the solution to this inequality. Take any number you want that's bigger than -1, plug it in, and this inequality will be true. Or take any number that's less than -5, plug it in there, and it's going to be true. What does that look like on a number line? It looks like this. Anything bigger than 1, not equal to 1, because it's not equal to, or anything less than -5. And these numbers will satisfy this quadratic inequality. Another one here, we'll solve algebraically. Isolate the squared expression, so subtract 1 on both sides. That 9 becomes an 8. Multiply both sides by 2, and you get a 16. We're going to square root both sides, so we get 4, because 4 times 4 is 16, or -4 times -4 is also 16, and notice that sign flips. So we're looking for numbers here that are, when we square them, they're less than 16. What number squared will be less than 16? Any numbers less than 4 squared will be less than 16, like 3 squared is 9, 2 squared is 2, 1 squared is 1, so on and so forth. But then we want to flip the sign because we also want any numbers that are bigger than -4. Like -3 is bigger than -4, so -3 would work in here because -3 squared is 9, which is less than 16. So once again, we have that sign flip, and when this positive becomes a negative, because that will satisfy this inequality that we have right here. Then we just take these two and we solve them algebraically. Add 5 to both sides, and we get x is less than or equal to 9, or x can be bigger than or equal to 1. When we graph those on a number line, it looks like this. So notice here, they're in between each other, because these two inequalities are kind of dictating that they got to be in between each other. We want x to be less than or equal to 9. We want x to be greater than or equal to 1. Those two are in between each other. So x, it has to satisfy both of them. So x has got to be bigger than 1, but at the same time, it has to be less than 9. If we go outside of this, this inequality will not be satisfied. And the circles are colored in because they could be equal to those numbers.